This video is the third in a three-part video that we're going to solve this elliptic partial differential equation that describes a fluid dynamics flow. So we're solving for the fluid potential, phi, that's given by this differential equation within this box with two sources and two sinks. In the previous video we talked about how we can discretize this equation, then we talked about how we could build the matrices that are needed to solve for this equation. So now we're going to write the MATLAB code that builds the matrices, solves for the potential, and plots the solution. So a couple of things to note: for all cells that exist on the boundary, there's a 1 on the diagonal. For any cells that exist on the interior, there's a -4 on the diagonal, a 1 on the off diagonal, and a 1 that's nx cells away from the main diagonal. So we're going to use that to build this M matrix. And the B matrix is going to be our boundary conditions for cells that exist on the boundary. It's going to be a 0 for cells that exist on the interior. So that's what we need to build using MATLAB. So now I'm going to switch over to MATLAB, and we're going to write a code that's going to solve this problem. So I'm going to begin by just writing a comment. So this is the code to solve a 2D elliptic PDE. And the first thing we're going to do is clear the workspace and the command window. So clear command space. Clear the workspace and command window. Then we're going to initialize things. So let's say inputs. We're going to have nx is equal to 50 in this case, so 50 grid points in the x direction, and y is equal to 50 grid points in the y direction. We're going to have a domain size of lx is equal to 5, ly is equal to 5. And these things you can change as needed. So we're going to create the grid. So the grid has x and y, so x is equal to, the way I'm going to create it is a lin space between 0 and lx with nx grid points. So that just creates equally spaced grid points between 0 and lx with nx of them. Y is going to be the exact same thing. Lin space between 0 and ly with ny grid points. We might also need a delta x. Actually, we don't need a delta x in this problem. But if you needed a dx, you could say that is the second grid point minus the first grid point. That's the way I like to do it, since they're all equally spaced. We can just do it that way. And dy may be y2 minus y of 1, if you need those. But those aren't actually needed. This is the mesh size. This is the actual mesh. Okay. Let's initialize our matrices. Since the matrices are mostly zeros, let's just create them as zeros. We need to know how many unknowns we have. So n is the number of known unknowns, and that's going to be nx times ny. So in this problem we have 50 points in x, 50 points in y, which gives us 2,500 unknowns. So this is the number of unknowns that we're going to solve for. And then once we have that, we can build our M matrix. So M is going to be an n by n matrix. So it has n rows, n columns. B has n rows, 1 column. And we're just initially create a bunch of zeros. We just put zeros in there. And now we need to fill in different parts of those matrices. I'm going to start by filling in the parts of the matrix that come from the interior grid points. And if you remember, if we go back to the matrix that we built, so these rows that are highlighted with green, those are our interior grid points. We need a -4 in the diagonal. We have 1s on the off diagonals and 1s way on the off diagonals, and they're nx points away. So that's what we have to build into our matrix. So I'm going to first of all loop over all of them. So interior points, I is our x index, and that we're going to go from n2 to nx minus 1. So we're going to skip the first grid point in the x direction and the last grid point in the x direction. So this is loop over the x direction, skipping first and last grid points. Then we're going to do for j is equal to 2 through ny minus 1, which is a loop over y. Direction skipping first and last grid points. Okay, then at each of those grid points I need to fill in the different parts of this M matrix. But first of all I need to figure out which row in the matrix I am. So let's go back to the matrix that we constructed before. So we're currently at the ij grid point, which for example could be 2, 2, could be 3, 2. But we need to know which number in this column we're at. So because we've taken our 2D representation of these unknowns and we've put that into a long vector, we have to know, am I the first entry in the vector, am I the second, third, fourth, fifth, sixth, seventh, and so forth. So I'm going to call that the nth entry, and we can compute n. So n is equal to, and I'm just going to give you the formula, it's I plus j minus 1 times nx, and this is to convert the ij grid point to the nth grid point. So we're converting our 2D grid to just this 1D column, and we're at the nth grid point. So when we're at ij, we're also at n. So we can go between these two. And at that nth grid point, we need to put a 1 on the diagonal. So we're going to be at the nth row, and in the nth column, I'm going to put a minus 4. So this is the main diagonal. We need to put a 1 on the off diagonals. So m in the nth row, the n minus 1 column, that is going to correspond to, so we put a minus 4 on the diagonal, n minus 1 is going to put a right here, so we need to put a 1 there. After that we're going to put a 1 at the n plus 1 diagonal. So let's do n minus 1 is equal to 1. This is the off diagonal to the left. And then we just put some spaces in here so everything is lined up nicely. And then we're going to do n, the nth row, the n plus 1th column also gets a 1. This is the off diagonal to the right. And we just put a couple more spaces so everything's nicely lined up, so it looks better. Okay, so far we've put the minus 4 in the diagonal, the 1's on the just off diagonals. Now we need to put the 1 way over here, which is nx points away from the main diagonal, and the 1 way over here, which is also nx points away from the main diagonal. So we need to put m at the nth row, n minus nx, it's a 1. This is the far off diagonal to the left. And we're going to have the nth row, the n plus nx column also gets a 1, which is the far off diagonal to the right. And let's go back to our matrix. So we did everything over here. We just need to put the 0 on the right hand side. For this problem it's kind of trivial because there's a 0 there, but in general that might not be a 0, so I'm just going to write the code that does it. So that's going to be in the B matrix on the nth row, the first column, because there's only one column, and that's equal to 0 in this case. So that I'm going to label as the source term. In this problem there's no actual source, so that's why we have a 0 there. I can just line things up a little. Okay, so 0 for this problem. In general, if you had something else there, that's where it would go. Okay, so that's how we can build the M matrix and the B matrix for all interior points. Now we have to build in boundary conditions. And we have to put boundary conditions on each side. So let's start with the left side. So let's say the left boundary condition. So the left boundary condition for this problem was that the potential, so phi, is equal to what did we say it was there? That's just y. The phi is equal to y on the left boundary condition. So on the left boundary, I is equal to 1, so I just know that we're at the first cells in the x direction, so I is equal to 1. And we're going to loop over all cells in j. So for j is equal to 1 through ny, we're going to loop over that whole left-hand side. And here, first of all, I need to figure out what's our n here. So n is equal to I plus j minus 1 times nx. And this just tells me I'm on the nth row for this ij. So I know my ij here. I need to figure out which row in the matrix I'm at. And once I know that, I'm going to fill in, let's go back to our matrices. So I'm at one of these boundary cells. And for the boundary cells, I need to put 1 on the diagonal. And then I need to put my boundary condition in the B matrix. So to put a 1 on the diagonal, I'm going to do n comma n is equal to 1. So this is the main diagonal. And then in the B matrix, in n comma 1, I put my boundary condition, which in this case is y of j. It's the jth y. So this is the boundary condition at yj. At the jth y. Okay, so that's how we can write the boundary conditions for the left side of our domain. So I'm going to copy this, and we're going to do the right side of the domain, because the right side of the domain is going to be very similar to the left. So let's say the right boundary condition. At the right boundary condition, our boundary condition is actually minus 1 minus y. So we need to put that in here. For on the right side of the domain, I is not going to be 1, I is going to be nx. And we're at the far right-hand side. I get my n, put a 1 on the main diagonal, so this stuff all stays the same. Just my boundary condition changes. Here I'm going to have a minus 1 minus y, the jth y. So there we go. We just did the right boundary condition. Let's do the bottom. So at the bottom we have phi is equal to minus x. Let me check if that's right. So let me go back here. Yeah, the bottom boundary condition is minus x, so we're going to use that. And on the bottom we know that j is equal to 1, and we're going to loop over all I. We're going to loop over I is equal to 1 to nx. We keep the n equation the same. We still put a 1 on the main diagonal. In the b, we're going to put our minus x of I, which is the boundary condition at x of I. Okay. I'm going to copy this code because the top's going to be very similar to the bottom. We're going to have the top. On the top, j is equal to ny. Still loop over all I. We still get our nth row for this ij. We still put a 1 on the main diagonal. On the top, we just fill in what our boundary condition is. On the top, we have 1 minus x. So here I'm going to have 1 minus x of I. And that fills in all the boundary conditions on all the sides. So now we've really built our matrices. And those should be exactly what we need. Now once we have those, we can solve for the potential, which is our unknown. So I'm going to say phi is equal to, you can write this multiple ways. You could say inverse of m times b. So what we're really solving here is m times phi is equal to b. If you multiply this by the inverse of m, you get phi is equal to the inverse of mb. Now in MATLAB, it's better to write this as phi is equal to m backslash b. It's actually, if you put your cursor over the inverse, it will tell you that inverse of a can be slow. Consider using a backslash b. So that's what we're going to do. We're not going to write this code because it's a little bit slower and less accurate than the second code, but they mean pretty much the same thing. So that will solve for our phi's. So if I go back to our matrix, we've just solved for all of these phi's. And we've solved for them in a big vector like that. So the last step is to convert that vector back into a 2D grid. So we're going to convert the vector solution to a 2D array. And the way that I like to do that is I just loop over the domain. So I'm going to do for I is equal to 1 through nx, for j is equal to 1 through ny. I'm going to loop over each grid point, and at that grid point, I'm going to figure out which row in that vector I'm currently at. So this, I'm going to use my n equation again. So this is the nth row for this ij. So I know that that's the nth row, and I can say that my phi, let's call this phi up here, maybe phi vector. And I'm going to say phi of ij, so the ij phi is equal to my phi vector evaluated at the nth row. So I'm just converting this vector of representation of phi into a two-dimensional grid. And finally, I can plot the result. So the final result is surf. I'm going to create a surface plot, x, y, of phi. I'm going to put the transpose here so that one quotation mark is takes the transpose, which converts just the way MATLAB represents vectors is a little different than the way that we think about them with this ij. So you need that transpose there to kind of shift things around. Maybe you want to put some labels on. So x label x, y label y. Maybe you want to make those labels a little bigger. So set GCA font size 16. So that changes the font size. GCA is the get current axes handle. So that's just the current axes, make the fonts bigger. Okay, so I'm going to run that. I'll save it. And it sounds like I got an error. So I got undefined functional variable b on line 66. So right here, and the issue is I've created a capital B instead of a lowercase b. So let me make a lowercase b there. And when I run that, here is my solution, which is rather interesting. So the reason that the result wasn't exactly what I was expecting is because I've actually wrote down my boundary conditions wrong and the domain size. So I go back to my original problem. This is what I told you that we were solving. And you'll notice that x goes between 0 and 1, when in my MATLAB code it's still currently going between 0 and 5, so I need to change that. And y also goes between 0 and 1. The other thing that I want to change, because I don't know how I made this mistake, but the bottom boundary condition, we're not going to do this. We're just going to have phi is equal to x on the bottom. On the left side, on the right side, we're going to just do 1 minus y. On the top, we're going to do 1 minus x, so that's okay. And over here, we're going to do y, so that's okay. I'm going to change the bottom and right boundary conditions and our domain size. So let's do that, and hopefully that gets me what I want. So change Lx and Ly to 1. So I actually already did that, it's from 5. I need to change the right boundary condition to just 1 minus y. So on line 47, I'm modifying that. And the bottom, I just want this to be x instead of minus x. So this is x, and this is just 1 minus y. If I run that, I get something that looks like this. And this is what I was expecting. So we have high potential on 2 corners and low potential on the other 2 corners, which, if we go back to our original problem statement, we have 2 sources with high potential and 2 sinks with low potential. So that makes sense, so that's our solution. It kind of looks like a Pringle, but that is our potential. This problem has a little bit of physical meaning, so in general this isn't general to most problems, but for this problem we can compute the velocity from the potential, and we know that the u component of velocity, so the component in x, is d phi dx, sorry, minus d phi dx, so this is the x component of velocity, and we know that v is equal to minus d phi dy, this is the y component of velocity. So we need to compute those, so I'm going to loop over I'm going to compute a velocity at all interior grid points. So I'm going to just say u is equal to zeros nx by ny, just v is equal to zeros nx by ny. I'm just going to create those arrays, and then we'll loop over all interior grid points and compute this velocity. So for I is equal to 2 through nx minus 1, for j is equal to 2 through ny minus 1. So this is loop over interior grid points. And then we're going to actually compute the velocity. So the velocity uijk here is, here I'm going to use my finite difference operator. So the minus from the formula, and then phi at I plus 1j minus phi at I minus 1j divided by 2 times dx is my u velocity. And my v velocity is going to be very similar. So I'm going to have v of ij is equal to minus phi of ij plus 1 minus phi of ij minus 1 divided by 2 times dy. So those are just finite difference operators for the first derivative applied in the applied to that problem, to phi. So I'm going to plot this. I'm going to do figure 2, create a new figure. Just clear that figure. And I'm going to make a quiver plot. X, Y, U transpose, V transpose, which a quiver plot is like we'll see in a second, but it's a bunch of arrows. It's like a vector plot, and we'll put some labels on there. And we put a title, the velocity field. So if I run this code, now you can see my velocity field coming out of, so I have velocity coming from the top left corner and from the bottom right corner, and then that exits the other two corners. So I have flow that comes in from the sides, from the two corners and out the other two corners. So that's my velocity field, and that's a quiver plot. So that's kind of a useful, an interesting extension of this problem, where once we compute phi, we can do something with it and compute the velocity field. But the real interesting thing that you should know that's generalized to most problems is what happens up here. So create your inputs, create the grid, and really generate the matrices. So what you do at interior points, how you put things on the diagonal, on the off diagonals, the far off diagonals. So this, everything in these parentheses actually stays the same. You might have to change what you put over here, depending on the problem. And then your boundary conditions. In general, most of this code stays the same. It's just what you change in here, where you're actually applying the boundary condition for that problem. So, and then you always solve for the unknown, and you always convert the solution back to a 2D array and plot. So that's hopefully a useful code to look at. Let me try just changing the font size to something small, so maybe you can see the entire code right like that, and I'll leave that as the end of this video.